So it's still a few minutes left, so I think we will wait for at least 1 more minute before starting. Someone is writing something, so maybe you can mute. Okay, it's 3 o'clock, and I would like to welcome all to this webinar on control of HVDC and fast frequency reserves in response to decreasing inertia. It's the first webinar in a series of 4 organized by the Multi-DC project. And I hope you have taken the opportunity to register also for the other 3, otherwise there's still time. My name is Segerqvist, and I will have the role as moderator at this webinar. I work at Hitachi-ABB Power Grids with system design for HVDC, and we are one of the partners in this Multi-DC project. I would like to remind you that this webinar will be recorded in case you ask questions. If you want, your name will be visible, whatever name you have registered under. And the recording will be available on the Multi-DC website in case you want to revisit it later on. Also, the slides from the presentations will be available on the website. It's usually a standard question. I will start with a few technical details. We are quite many on this call right now, 94 attendees. And so all participants are muted except for me and the speakers. But we really want you to participate and ask questions. So please use the Q&A function or the chat. And we will do our best to try to keep up with the flow. Each presenter will have a presentation for about 10 minutes. And there's room for a few clarifying questions. So don't wait to post a question. And after the presentations, there is room for discussion. And also there, we would like to have comments from you on topics that you would like the presenters to discuss or elaborate around from the earlier presentations. Yes. A few words on Multi-DC, controlling the power flows. This project is funded by Innovation Fund Denmark Grant Solutions, with the aim to build up the know-how in the energy sector with focus on energy islands, zero inertia offshore grids, and optimal coordination of HVDC. You can see the partners listed on the slide, and DTU is the leading partner. The program has run for 5 years with a budget of 3.5 million euro. And I would like to remind that on October 28, there will be a demonstration event at the DTU Lyngby campus. And if you cannot join live at location, it will be also broadcasted live. So you can join from wherever you are. So in this webinar, we will have the opportunity to listen to 4 interesting speakers. They represent 3 different systems: Great Britain, Texas, and the Nordic. And we have a common slide that we just want to show before starting. And as you can see, there are both differences and similarities within these 3 systems. For instance, even though the system loading seems to be rather similar, there's quite big difference in reference incident if you compare Texas to the other 2. And yeah, you see there's also what is the main challenge, drop-off or instantaneous frequency minimum, for instance. So think about that also when you listen to the presentations. I think it will be interesting to hear how the characteristics of each system impact the current status and the way forward regarding frequency control and decreasing inertia, and of course, what role HVDC can play. Yes, and now our first speaker is Benjamin Marshall. He's HVDC Technology Manager at the National HVDC Centre in Scotland, UK. And I will switch over to his presentation. Yes. Soon. Nej.
Thank you for having me. I am Ben Marshall. I'm the Technology Manager here at the HVDC Centre. So if we move on to the next slide, Inga.
Sorry. Yes. Sorry. I will try to make it big. Can you see my screen? Or?
I can. Yeah.
Okay, good. Yeah. It doesn't really look like that on mine.
The challenges of getting used to the world. So yeah, a quick sort of burst of who we are, because I'm conscious many of you won't notice we've even got people from Mongolia. So the National HVDC Centre was set up in 2013 as part of an innovation project within She Transmission. The transmission owners within GB. We look up after the also, we work in partnership with other transmission owners, both National Grid, the GB Electricity System Operator under a license, and SP Energy Networks, who operate distribution and transmission. What's the centre? What is it there for? Well, essentially, the centre is a high granularity simulation environment, which deals with both real-time and offline, predominantly EMT analysis. And so we are a repository for experience and commissioning and de-risking activities associated with large HVDC fax devices. So we provide a variety of tools for analysis, both in terms of the platforms, but also a number of techniques that we develop. We also have a number of inputs into systems, standards, R&D that goes on within the industry. And we also provide a range of structured training and research into converter design, control, and its implementation. So if we move to the next slide. Just a brief introduction to the topics I'm going to cover. A bit of what is frequency stability, what influences that with the GB focus, moving towards where we're talking about HVDC, what does it do, how does it implement response, and then we move on to the future of HVDC and large-scale power electronics, and then we round up by talking a bit about future risks, in particular interoperability with the key area as we move forward. So moving to the next slide, what are the key issues in frequency? Well, one issue as we move towards inertia. So you noted on the slide that we talked about a minimum inertia of around 140 GVA seconds. We have a frequency policy within GB to try and operate minimum inertia of GVA seconds, which means intervention in order to maintain that minimum. It also means that we're also to manage assets market minimum, which could be down to as low as 96, or in the future closer to 50 GVA seconds. So there's both market interventions, transmission interventions, and keep you at that GVA second. In a system which peaks at about sort of 56 gigawatts in the past and can be as down as the low teens in terms of its demand, it's quite manage the inertia quite carefully. Maximum loss is currently somewhere between 8 megawatts and typically. So what you can see is that the system with a relatively low inertia will move around a little, and that's just natural because of the supply and demand balance on the system. So it's going to see perturbances which are going to move faster in the low inertia system than in a high inertia system. All of the frequency response is focused on maintaining those operational limits that you can see to the top right, the 49.8 to 50.2 region. There's also a question of responding to a frequency that happens as could be incurred in the system. We contain those losses to a maximum of 1800 megawatts, but where they happen and how they then perform from inset middle there, the frequency can be different in different parts of the GB system. That's a key kind of point for the GB network, that you can see as much as a 20% difference across the network between values. And you can also see significance of the absolute frequency. So that needs to be borne in mind, because increasing, we're moving towards faster and faster. Is that a response too?
Sorry, Ben. Just to tell you that there is a problem with your sound that is just fluctuating, so we can hear you and then we lose. So would you prefer?
Apologies for that. I'll go on to just audio only, maybe, and that may help a little.
So you can try to fix that now, or if you prefer, we can maybe continue with the next presenter. And then maybe you can continue when you feel like you fixed the issue.
If you prefer to do it that way, Danilo, of course we can do it.
I don't know. It's maybe Inger. What do you think? What's the best option?
No, I think you don't have a headset or something that you can use. Maybe it's the microphone itself, because maybe it's better than we can.
Let me see what I can do. If you jump to the next presenter, I'll come back.
Yeah. Okay. So
right,
then,
thank you.
Thank you.
We apologize to the audience. Yeah.
Yes. So then the next speaker would be Julia, and I must admit I have a bit of problem to pronounce your family name, so I think I will not. I will stop sharing. I hope. Yes. So Julia, if you can start sharing. Thanks.
Can you see it in full screen now, or presenter's version?
Presenter's version.
Okay, so just the screen is better.
Yeah, it's better. Thank you.
All right. So my name is Julia Matevosyan. I'm lead planning engineer in ERCOT. So I'll jump straight in. I have here Inertia Plot. Wait a second, I'll turn the camera on as well. So what you can see here is a box plot for inertia for the past 7 and a little bit years. So the box plot is showing 25th and give me a second, I'll get the pointer. So the box is around 25th and 75th percentile of system inertia in a year, and the whiskers are showing 2.7 sigma of the distribution, assuming that's a normal distribution. And then red line is the median. And then these dots here, they are showing instances when the largest share of load was served by wind generation in each year. Why am I only talking about wind generation here is because our system, the main concern with inertia happens at nighttime when load is low and wind generation is high. So our wind generation peaks at nighttime in spring and in autumn months. So in blue here, you can see how much wind generation we had at the end of each year. So it kind of puts it into perspective, and you see that we added about 20 gigawatt of wind generation from 2013 through 2021. This data set ends in July here for 2021. But now if you look at inertia, you can see that inertia trend barely changed. And this is not what we expected. We anticipated that with such a large addition of inverter-based resources on the system, that that inertia will decrease at about faster trend. But that didn't happen, and this is because of several different factors like load growth, and we have low gas prices, which results in switch between coal generation and combined cycle generation. And so combined cycle generation has higher inertia than coal, and so as it replaces coal generation in the generation mix, we get actually increase in inertia. And then some of this wind generation is curtailed because of transmission constraints, and so we don't get production from everything from 100%, what's installed. So we keep monitoring this trend. We monitor inertia in real time, and we expect this trend to keep declining in the future because we keep adding wind, and now also solar generation is picking up very quickly. We also determined critical inertia level, so inertia floor, if you will, and that is inertia level that we need to keep on our system so that with existing frequency control measures, we can arrest frequency before it gets to under frequency load shedding trigger. And so currently for ERCOT system, critical inertia is 100 gigawatt seconds, and system operator will take measures to keep inertia at this level if it gets close to it by bringing additional generation online. So in ERCOT, we have a responsive reserve service. This is an ancillary service that we use to provide frequency containment reserves after a large generated trip. And as you have seen in this table that Inger showed in the beginning, we need to protect for loss of 2 nuclear units at the same plant, and which is altogether about 2805 megawatt. And we have, I noticed compared to other systems, we have relatively narrow frequency band that we need to regulate in, and our under frequency load shedding happens faster than what's UK and Nordic colleagues are showing. So this responsive reserve service for frequency containment can be provided by three components actually. So first one is through primary frequency response. So this is your traditional governor response from generation resources, but ERCOT also allows controllable load resources and storage to provide in this subset. So they controllable load resources and storage, they provide similar type of response that looks like governor response. And we have 17 millihertz deadband and maximum 5% droop. So droop can actually be set lower than 5% if possible. Then we have load resources that provide responsive reserve service. They have high set under frequency relays that will trip this load at 59.7 hertz within half a second. So this is in a way already fast frequency response that we had previously for many years now. And this load resources can provide up to 60% of total responsive reserve requirement. And then we have resources capable for fast frequency response. This is a new subproduct that only was added in March 2020. And so this is what I will focus on for the rest of my presentation. I also would like to mention that amounts of responsive reserve that we procure depends on inertia that we expect for the next day for a given hour. And participation of fast responding resources affects the total amount of responsive reserve that we procure. And this is because at low inertia, faster reserves are more effective. And so we can procure less total amount if we have more participation from fast frequency responding products. So what's fast frequency response? I have a bit more details about this particular product because it's new and focus of my presentation. To be qualified for provision of fast frequency response, the resource should be automatically deployed and provide full response within 15 cycles. So this is a quarter of a second in the US because we're 60 hertz system. And then after frequency drops to 59.85 hertz, we'll get step response from this FFR product. Resources must sustain full response for at least 15 minutes once they're deployed. And they should not recall their response until frequency is greater than 59.85 Hertz, or deployment lasted for over 15 minutes. So this recovery frequency or 15 minutes, whichever is faster. And then once recalled, fast frequency response reserve should be able to reassume their responsibility within 15 minutes after the cessation of deployment. So this means they have to return back to service within 15 minutes. And this is geared more towards batteries, meaning that they're supposed to be recharged and capable of providing FFR again in 15 minutes after previous deployment. So this chart here, it shows for different response time in cycles, and again, remind you we're a 60 Hertz system, how much critical inertia can be decreased. So basically currently, or before introduction of FFR, we were here, we had our fastest frequency containment reserve was load resources that deploys within half a second, so 30 cycles. And our critical inertia from the calculation, it's 94 gigawatt seconds, but we actually set it at 100 to give it a little bit of margin. And so as we went to 15 cycles, and once FFR product is fully subscribed, we can actually go to 84 gigawatt seconds of inertia, and with a little bit of margin, it will be set at 90 gigawatt seconds. So basically having faster response allows us to reduce critical inertia or inertia floor. And that means less commitment of synchronous generation just for the purpose of inertia. So for the next two slides, I have a little bit of explanation why we have the settings for FFR. So here you can see historic events, frequency events that happened, and you can see how far they went in terms of frequency on the x-axis, and then the size of event on y-axis. And you can see that with 59.85 Hertz trigger, we basically probably address about a third of frequency events that are happening. So we intend to use FFR for larger events, but also not as large as what would trigger load resources, because we would like to keep load resources for extreme events when really large generation trips. Then the second chart here shows the duration of frequency events in ERCOT, again, for the same period of time in history. And again, loss in megawatts is on y-axis. And you can see that frequency events barely last 15 minutes. So all of the events are shorter than that. And that should be reassuring for batteries providing FFR. That means that barely they will be ever deployed for entire 15 minutes. And most of the events are less than 8 minutes. One thing to mention too about the recall and returning back to service, load resources once deployed, just to the nature of the industry, they may not return back for 3 hours. And this is where FFR would be really helpful, because if load resources deployed, we're exposed and we have less reserve for 3 hours, but FFR will be able to return back to service within 15 minutes of deployment. So this is kind of a safety net for us. So this slide here shows reduction that we can achieve by introducing FFR product into a responsive reserve service mix. Just a reminder, this is total RRS amount, and this is inertia. As I said, the total RRS amounts varies with inertia. And the difference here that you see, it's basically from replacing load resources that are already providing fast frequency response with even faster frequency response from FFR. So that's why the gain is not as big, but the gain is much bigger because both load resources and FFR are substituting frequency response provided through governor response from generation resources, and faster resources are more effective in low inertia conditions. So this is the gain here is just between, from the speed of response of FFR compared to load resources. There is some gain still. And so this is next to last slide here is just showing that because we went for step response, There is an overfrequency concern because if we trip too big amount or we get step response from too big amount during just as we hit 59.85 trigger, we can go into overfrequency. So we have done a study to determine a limit for FFR to avoid overfrequency event. So we find the smallest or the largest megawatt loss that takes us straight to 59.85 frequency trigger. And then we trigger FFR and we see how much we can trigger safely without hitting overfrequency concern. And so we found that with that, we need to set a limit of 460 megawatts on FFR. So in conclusion, FFR arrests frequency decay faster, and therefore we can reduce critical inertia, and this provides savings because we don't need to bring additional synchronous generation online just for inertia, and we can accommodate more renewable resources in the generation mix. FFR ensures that load resources remain available for more severe frequency events, so it provides increased reliability. It leads to reduction of overall responsive reserve quantities, so it's cost saving. And as I mentioned, step response from FFR leads to relatively low FFR limit and limits benefits from FFR. So some efficiency can be achieved by going for proportional response. And with that, thank you very much for your attention.
Thank you, Julia, for a very interesting presentation. And there are several questions, actually. I'm not sure if we can take them all at this point, but we will save them for later on. One is a discussion on how to measure inertia with what unit. I think maybe we can save it for afterwards. But and then there's one on how inertia is estimated or predicted for the market. Do you have some feedback on this?
Yeah, so maybe I can actually start with how we measure it. We have telemetry from every generator on our system. Most of generation is connected at transmission level. So we receive 4-second telemetry about generator status, and we have a lookup table of its inertia parameters. So we basically just sum up inertia of all units that are generation units that are online at any given time. So that's how we get it in real time. And then for prediction of inertia, we get from every generator, we get a current operating plan that shows what this generator is going to do for the next 168 hours. And one piece of information is if they're going to be online or offline for the next 168 hours. And we use that information to forecast inertia. So we just look up if a generator is going to be online, we match it up with its inertia contribution, and then we calculate total inertia contribution. These current operating plans are updated every hour and then again spend 168 hours. And so they are more certain for the first 24 hours, and then they may change as we go forward, but we basically use inertia prediction, maybe just looking about 3 hours out.
Okay, yeah, thank you. I think we move on to Robert, who is the next presenter, and then I will try to sum up the questions for the discussion later on.
All right.
So, yeah.
Thank you.
Robert, are you available?
Yes. Share screen. Okay, good. So my name is Robert Eriksson, and I work for the Swedish TSO, Svenska Kraftnät, and I'm involved in several R&D projects, and I'm also involved in stability studies. And this talk will be about frequency stability in the Nordic power system seen from a TSO point of view. When people speak about frequency stability, a lot of focus is usually on inertia, but it's also important to keep in mind that frequency stability is actually affected by 3 different things. So we have the inertia, of course, but we also have the reserve, so the speed of the reserves, and the imbalance that can occur. And this table was previously shown by Inger, and for the Nordic system this summer we got a new record in low inertia, and we reached down to 110 gigawatt seconds. And also recently we have commissioned 2 HVDC links in Norway with the rated power of 1400 megawatts that could be reference incident for over frequency. For under frequency, we still have a nuclear power plant of 1450 megawatts as the reference incident. And the main challenge in the Nordic power system is the instantaneous frequency minimum. So traditionally, the reserves in the Nordic power system have come from hydropower. But since we are phasing out nuclear power plants and we are replacing other synchronous generation with wind power and PV, we reduce the inertia, meaning that we have to make the reserves faster. But since we have a lot of hydropower contributing to the reserves, there is of course a limit for hydropower to be able to fulfill the system needs. So how fast can you make the response of hydropower, both in terms of how you can actually control the unit itself, but also will you maintain stability? I mean, closed loop stability, will you sort of get an oscillation in the frequency after an event if you make it too fast? So what we have then implemented in the Nordic system is the fast frequency reserve, but we are also looking into synthetic inertia because we see a need for that in the future. So this is an estimation of the inertia in the Nordic power system. So this is based on market simulations that we have done. So on the axis here you see inertia, and down here it's time per year in percent. So this area is then of concern, so meaning that we have low inertia. And the upper 2 curves here are for 2020 and for 2030. And then for 2040 we see that the inertia will be reduced quite a lot. And I believe actually that these numbers are a bit optimistic. So perhaps we will see even lower inertia values rather soon. So the Nordic fast frequency reserve was implemented 1 year ago. So for summer 2020, we implemented this. And the reserve is constructed in a way where it should be a step response. When the frequency reaches 49.6, it should be triggered, and then the amount should be activated in 1 second. And then we have 2 options for duration, one that is 5 seconds and another is 30 seconds. And we actually also have variation of this full activation time and this trigger level, but this is sort of the standard product. And depending on how the unit ramps down, they can select between a short duration and long duration. And potential providers of this reserve is then loads, energy storages, HVDC, and wind power. And we have seen that we have a need for up to 300 megawatts of this reserve. But of course, it depends a lot on the hydrological situation. So depending on how much rain we get every year. And so far, we have natural markets in the 4 countries. So how do we monitor frequency stability? So what we did was that we collected the various events that have happened in the system, and we made a dynamic model based on these events. So we were mapping this data to a dynamic model and then implemented this in the control centers. So the control centers will then see what would be the lowest frequency in case of the worst n-1 trip. So we have to monitor the inertia and the reference incident to be able to make this calculation. So this is then seen in real time. But how do we then ensure frequency stability? Well, we need a forecast of the inertia. So we made a forecast based on machine learning, taking the market information into consideration. And based on that, we can get a forecast for almost a week. But of course, the closer you get in time, the better the forecast is. And we also need a forecast of the reference incident. And that one is usually quite easy because we have the market information from the nuclear power plants and also usually from the HVDC links, how they will operate. And based on this forecast, we can then calculate how much fast frequency reserve we need. And then we procure that in the countries, the national markets. And we can also ensure that we have capacity on the HVDC links for EPC activation. So EPC is then emergency power control. So this is at the moment sort of a backup in case we are not able to procure fast frequency reserve. I was also taking part in an NSOE project a year back where we were designing how we should exchange reserves over HVDC links. And this exchange was focusing on this limited frequency sensitivity mode, which is then a fast primary reserve that would kick in if the frequency drop is quite high in the different synchronous areas. So here you see that we have a proportional controller for this. So this is also like a fast frequency reserve, but with proportional control. And in this study, we were simulating how much in total power you can exchange between the different synchronous areas without deteriorating the frequency too much. And for the Nordic countries, for under frequency, there is a support of maximum 1,600 megawatts from UK and from the Central European system. And for over frequency, it's 1,400. And similarly, we have for the continental European system and for Great Britain, how many megawatts that can be exchanged. So this is under implementation. So soon we will have this implemented on the HVDC links connecting the synchronous areas. And challenges that I see for the future is that there is a trade-off in the HVDC capacity, meaning that what should be reserved for reserves and what should be reserved for the energy market. Until now, most of the capacity has been given to the energy market. But I see that in the future, we also need to be able to exchange reserves over HVDC. And also we are going to exchange the slower reserves in terms of MFR and AFRR over HVDC. Meaning that if you have a lot of reserves exchanged, you need to see what is allocated to which reserve. And we have also looked into the possibility to use overload capability of the HVDC links, meaning that you can actually overload the HVDC links for a short time, maybe 10, 15, 30 minutes, depending on the technology. And that we have implemented right now in one HVDC link, but we're also looking into that for other HVDC links. And also it's a bit complicated to agree with all the different TSOs, how we should exchange reserves and the amount. And I see that is a challenge as well. And some HVDC links also have old control systems, meaning that perhaps this droop-based control cannot be implemented. And instead, a step response can be used. But that is not so good for the other system that is providing the service, that the frequency will drop even further. Danilo will present more about that. What we're looking into now is how we can optimize the different reserves, and we're also developing new reserves. So we want to optimize the ratio between inertia, synthetic inertia, the stepwise FFR, which I call the FFR 1.0, and the future FFR 2.0 that would be proportional, and also how long the support should be from these services. So this is something that we look into at the moment. So that was this. Thank you.
Thank you, Robert. There's actually a few questions for you also. One is about the droop. It's Leon Kai who actually asks, did you activate the droops on your HVDC links?
We haven't done that yet, but we're implementing that soon.
Okay. And regarding this overload that you talked about, how long in second and how much per unit for the overload capability on HVDC links from?
It really depends on the technology. Some sort of have almost zero overload capabilities, but others, like the older LCC, I think we have like 20-30% overload capability for half an hour or so.
Okay. And then there's finally one question about experience in the Nordic regarding loss of HVDC link, if there has already been some experience in that for overfrequency.
Yeah, we had a trip of an HVDC link like 1 year ago during commission. It was actually first over frequency, and then it went back and was transferring power in the other direction. So first we had over frequency, then we had under frequency within just 1 minute or so. So it has happened.
Okay. Well, there's also more, but I think we will save them for later and give Danilo the chance to have his presentation.
Hello. So maybe it's a good idea to try out with Ben's presentation just to see now. If not, then I will continue, and then he will have more time to fix.
Okay.
Is that okay, Ben?
Okay. Can people hear me any better now?
Yes.
Now it's perfect.
Lovely, lovely. Get the added joy of seeing me look like an aircraft controller. So if we go back to the slide deck, then I think we were on slide 3. I'll try and rush through things and not delay too much. Sorry for the challenges here. Hi, Inga. Are you showing the slides? Yeah, that's great. Lovely. So we talked about frequency drift and how that's a function of the inertia on the system. Responding to frequency movement is clearly tuned to the level of inertia on the system, which defines the speed at which fast frequency response can act. As the slide indicates, because the frequency is different in different areas of the system, we have to be very cautious of how frequency response is handled in practice, because you can end up with differential responses which can aggravate inter-area modes across the network. And we also have a requirement, therefore, to damp an event, which requires us with an RSQSS to achieve a 12-second angular oscillation damping. So 12-second time constant, that is. So effectively bring a reduction of quarter amplitude within 20 or so seconds. And we also try and manage extreme events when they happen with further low frequency demand disconnection capability, which allows for cascaded events to be managed. So the key ingredients today are the system inertia itself. So building on some of the quick Q&A we've had earlier, within GB, we not only take into account the transmission connected generation inertias, which we hold, but we also attempt to estimate the level of residual inertia on the system. And we do that in two ways. One is via looking at previous events and trying to understand from that the inertia contained within distributed resources and the demand connected. And we also use active monitoring systems. We're trying two different approaches to inertia monitoring. One relates to the use of PMU data to look at signatures of oscillation and from that derive inertia. And another relates to injecting a signal and then from that signal deriving an understanding of the inertia. So effectively using very large supercapacitors as a form of load disruption that you can then trace the signal of throughout your system. So the latter approach of using those large load banks gives you a national view. The former using PMUs can give you an idea of your distribution of inertia, which in understanding the differential nature of your frequency following an event becomes quite important. If we move to the next slide then. So just to talk through some of the services that the ESO makes use of, and you can see here some of the results which have come through from the roadmap towards net zero, articulating how response is constructed today. So we make use of what's known as an enhanced frequency response service, which is occurring within 1 second of an event, and mandatory frequency response, which is activated within 2 seconds of an event with primary and secondary response, traditionally formulated around the capabilities of synchronous generators. We have firm frequency response, which can relate to fixed elements of response on the system that are enabled at given settings. And we also have dynamic containment, which again is a still faster form of sub 1 second response that enables events to be very rapidly responded to, counteracting based on the rock-off scene, the speed at which that response is then delivered. Now, those services, including other specifics to technologies such as hydro spin gen, low frequency response, interconnector response, which is generally contracted separately, and hydro pump deload, are being kind of consolidated into a set of product characteristics involving the dynamic containment, which is the very fast services that have been explored to date, and what's known as dynamic moderation, which is to deal with the damping effect, and dynamic regulation, which is to deal with the frequency drift issue that we discussed earlier. So the intent of this is to deal with the symptom, which is essentially as the inertia is falling, your frequency will move more quickly and it will move more frequently. So in any response which is quick, you're going to inject oscillation into that response, which requires a further moderating response to dampen the effect and to manage containment in the latter stages. So essentially the intent of this collection of services is that it allows you to move to still lower levels of response and an ambition to move towards, still lower levels of inertia, and ambition to move towards a 96 GVA second level has been expressed. And essentially this is mirroring what's happening with technologies. So increasingly we're getting technologies such as wind, such as batteries, such as interconnectors capable of very fast responses. However, these are services which would not inherently come with inertia. And in terms of the GB system, the legacy is that we've got a number of system referencing initial converters, which are around 20% of the overall volume. About 80% of the converters connected to date have some degree of frequency response capability, and around 50% of the converters have that potential to potentially retrofit with faster and more capable responses over time. So the GB system is really moving towards an emergent world where by 2025, the expectation is that we will be managing points in time where there's close to 100% renewable technology, which will include some nuclear. So there will be some inherent inertia on the system. But when you look at a sort of nuclear fleet, which is going to be in the region of 7 to 9 gigawatts by that stage, that's a very limited contribution towards the overall GVA second target that's required on the system. So that residual needs to be coming from other sources, be they use of synchronous condensers or use of converters providing grid forming capability, and some additional degrees of hydropower storage or spinning reserves of run of river. So if we move to the next slide. So what's going on in the future? Well, stability pathfinders.
Sorry for interrupting again. Inge,
Hi.
can you maybe somehow increase the size of the PDF or zoom in? At least zoom, because we see that the PDF is not maximized. And
yeah, I mean, I guess people will be seeing these slides in due course. So
can you maybe try to zoom in?
Let's see if we can do something there. And also it's worth saying that if you click on the screen and then roll your mouse, you should be able to achieve some degree of zooming yourself. That's a trick I'll use myself quite often. In terms of the future, if you look at the stability pathfinders that the ESO has introduced, one of the focuses is around looking at a distribution of inertia around the system. You can see there is a number of areas in red where inertia levels are particularly moved in terms of the drivers for stability, both because of the location of the inertia, the scale of the demand and the transfers is driving a particular need. And you've also got other areas in amber where the need is less pronounced. Now, I've summarized the requirements in GB at the top there, and there's about another 9 gigawatt seconds being procured. And this is against the target of the next couple of years. So in GB, we want to have that in place by 2024 across England and Wales, and around 2023 across Scotland. And one of the interesting things from the first set of tenders, which have been concentrated in Scotland, is the contribution of technologies that have come from non-synchronous technology. So only 33% of the contributions have come from synchronous technology. Now, the technical specification has some particular requirements around the net zero ambition and minimizing carbon production, and indeed ensuring that there's a flexibility in the amount of megawatts you need to bring on with your inertia. And maybe that's had an influence on that kind of proportion in the blue. But the vast majority of solutions are either hybrid or indeed grid forming converter solutions. So I saw one of the questions was around synthetic inertia. I just want to emphasize this is not what we're talking about. We're not talking about fast response here, because the core issue, as was summarized, is the rate of change of frequency we're seeing. So when you have a rate of change of frequency, that's the second derivative of your angle movement. Your converter is operating with a current loop control, which is trying to track the voltage angle on the system across any disturbance. And fundamentally, the challenge in a low inertia system is that the local angular movement is extremely quick and can become very chaotic based on the combination of the low inertia and the low short circuit level, bearing in mind that there's no such thing as an event which is purely frequency or purely voltage. Most are a combination of the two factors. So the grid forming solutions need to be robust to that, in particular robust to multiple events, to phase step movements, and delivering solutions which, irrespective of the location of the fault on the system, are capable of holding the angle of the system. So these are solutions which are seeking to provide time for more conventional forms of frequency response to activate and exist. It's important to note that as you move towards lower inertias on your system, you do need to think about new paradigms about how you control frequency. It's not just about frequency measurement anymore. So another point would be to identify where we're going. So the picture in terms of offshore coordination that you'll see in point 2, it really relates to the scale of converters that are coming onto the network. So by 2050, the estimate is in excess of 83 gigawatts, of which the vast majority, so 60 gigawatts plus, would be converter-dominated resources. Now, as I said, the demand on our system peaks at only 56 gigawatts. So you can see across the 2030 to 2050 period, we're going to get some very significant converter penetrations. So the use of grid-forming technologies surrounding those converter penetrations becomes critical. And it's about making sure that the wind farms and indeed the converters themselves are providing this grid-forming capability to ensure that you have that ability to slow down the onshore AC system frequency and coordinate your resources. And where I've put the blue arrows is kind of the key locations where large converters are coming on the GB system, which just so happen to be locations where you would have in the past seen very strong anchor points of large traditional inertia on the network. So you can see there's a coincidence, there's an opportunity that we need to agree at. And part of the delivery of these solutions, when you've got a large contribution of inertia, whether it's from converters or it's in the case of conventional products, is the conventional tuning becomes different. So lower inertia means more oscillations on your network, more degree of coordination. So wide area informed solutions become critical. And they need to, like the enhanced frequency containment control, which was suggested by an ESO NIC project, they need to be looking at a supervisory approach to looking across the network and bringing resources together with sufficient coordination, with sufficient delay for controllability and some course correction. So there are various approaches that are being explored at the moment, and as we evolve towards our 30 and 50 targets, are likely to increase in pace. If we move to the next slide. So in terms of the risks, and also, I've raised really 3. So the first one is guarding against new vulnerabilities that you'll see summarized on the right. Various points of single point failure, vulnerabilities in terms of controls, hidden project interactions, hidden project behaviors which are not being captured by models or codes or data exchange. Another issue is around the issue of last man standing. So your synchronous resources still exist. They still conform to equal area criteria. They still conform to the control limitations of a synchronous generator. So where you're getting large phase steps on the network, your synchronous machines can only respond and can be destabilized. You can drive pole slipping of those resources if you haven't got the right control strategies of your non-synchronous connections. So where you're delivering solutions such as inertial solutions, you need to be very cautious of ensuring that where you're having to introduce current limiting, which is almost inevitable in those solutions to guard against the rating of the converters, you need to be comfortable you're not introducing phase disturbances which are going to destabilize your existing synchronous contributions, and the devices such as PSSs are being aligned with them. And that kind of leads me to my final point about interoperability, which is that as you're getting more complex concepts, you need to have an ability to bring that detail together to understand the completeness of the control design and make sure that you're not missing anything. And that's really quite critical now at scale and pace. It's not something new, it's something that has been done within vendor facilities, within factory acceptance tests, combining control hardware with simulation depth, but the extent of simulation that you now need to do and the extent of hardware you now need to integrate is increasing dramatically, and that confirmation is really important to make sure you've got the right models for the right purposes and you're using them in the right ways. So my final kind of closing points will be on the last slide.
Yes.
And it's really about making sure that we're managing the information gap in the right way. So we're used to a world which is kind of in the top left insert, where I will tell you how I want to meet my requirement in the TSO world, and a vendor will tell me how he thinks he achieves that, and he'll sort out the gaps in between. And that's worked because conventional understanding of a classical power system has meant that you can fill in those gaps quite readily. However, in a non-synchronous dominated system, there are far too many variables, and what the manufacturer is trying to understand is really quite critical to how the TSO needs to operate. fundamental limitations of protection to guard against overcurrent or overvoltage in a DC rail make a difference in terms of the performance you can expect to see as a TSO. And there will be conditions that from a TSO's perspective, you would have expected inherently your synchronous fleet would have responded to and been resilient to, which are now no longer present in a converter dominated system. So the right way to deal with this is to talk about what you're trying to achieve, but also why, and to understand from the vendor what information he needs in order to achieve that solution and why he needs it. And that will illuminate to the TSO environment what issues it needs to be managing, which are above and beyond its conventional classical ones. What it drives you towards is an environment where you can bring complete data together, and across a number of organizations, not least AMO, and in the States, the recently announced initiative to look at integrating converters. There is a lot of exercise around what are known as hosted environments. This is where you're bringing together your detailed offline EMT environment and indeed your detailed real-time environment and comparing the two, ensuring that you're getting complete understanding and then feeding that back into the FAT. And on that point, I'll conclude, because this is what you need for future overall frequency control, that level of granularity.
I think you're painting up a very interesting future for engineering in power.
Oh,
Benjamin.
yes.
Yes.
Yes, we'll have plenty to do.
Thank you for that. And then, Danilo, I think it's your turn to do the presentation. So let's move on, and then I will try to sort up the questions for the minutes that we have at the end. Thank you, Benjamin.
All right. I'll try to hurry up a bit to go back on track. So hello, everyone from my side. My name is Danilo Obradovic. I'm a PhD student at KTH University in Stockholm, Sweden. I'm going to present part of my research work related to assessment of HVDC frequency control methods. In the beginning, I will give small introduction, and then in the first part, I will focus on HVDC emergency power control assessment or design. First, I'm gonna present the studies related to two different control methods in single mass system and show how they are implemented as well in the large multi-machine system. And then in the second part, I'm going to slide away a bit from HVDC and talk about also other properties affecting frequencies response, such as load modeling and PSS design, which is part of some kind of current work. And it might be also important for this frequency control. As you know, with the inertia reduction, we have a problem of controlling the frequency, as you heard, especially for large disturbances. And in this work, we are going to assess the control from HVDC links in a form of emergency power control or EPC. And the most important property for us is instantaneous frequency deviation or IFD, but also in this case is the closed loop stability margin of the given system, because that is seriously jeopardized from the inertia reduction. There are mainly two different methods that we compared here. One is sort of open loop method, ramp step EPC, where basically frequency serves as a triggering level. So when the frequency goes below a certain value, you start injecting ramp with a constant rate in terms of megawatts per second. And in the other case, frequency sort of a continuous input. It's a droop frequency based method where power output is proportional to your local frequency deviation. And as you can see from the map, there is a plenty of potential for Nordic power system to use their HVDC interconnections for frequency support. Initially, when we got this task from TSOs, we saw that each HVDC link participating in EPC has its own unique control settings. And they are stated 15, 20 years ago, and now some adjustments were needed. So the first, since they wanted to keep, first idea was to keep the same control method. So then we tried with simply just stating the unique activation value. So then we can identify how different activations affects the response. And then we could also summarize the ramps because they're activated at the same time, and then identify which control settings actually give us the instantaneous frequency deviation that is acceptable. Of course, the problem here is that this is not a closed loop method, so you don't improve the closed loop stability margin, even though you satisfy the IFD. Then we wanted to check true frequency-based EPC, and we did similar studies that were, for example, for different kinetic energies in the system. Of course, with the same base, we were testing how much gains in terms of megawatts per hertz, we need to keep again the IFD within reasonable limits, and we identify the settings that are needed. And then when you actually compare the settings that fulfill these requirements, here you can see 3 different responses. The first one were currently implemented in the Nordics. The second one are now some adjustments to equivalent activation and so on. And the other one is dual frequency based. What you can see is that all of them, even for low inertia value, are able to keep the IFD within the limits. However, this attenuation of frequency is very problematic for a stepwise activation of your EPC, and therefore dual frequency based performs much better in that sense and basically improve the closed loop stability margin, which can be shown. Then we decided to, in multi-DC project, to build this big power factory model, where basically we have we modeled wind power in future wind power integration onshore, offshore. We have HVDC links, VSCs and LCCs. We also understand how load modeling is important, and then we try to test all these methods to compare them. And the same dual frequency based methods was overperforming the stepwise, and therefore here we tested the dual. You see some results of the dual frequency based DPC, and basically you are able, even in this case, that if you provide enough gain, your frequency response becomes better. And you're also able to also replace some part of FCR with the EPC. It's just a question TSO would like to do that. On the other side, if you talk about some proper distribution of EPC actions and some optimization, that's a totally different problem, and that could be quite tricky to solve. And then what we were also investigating, since we were testing this big system, we noticed that apart from these standard properties that affect frequency response, we also see that voltage dynamic is quite important, that load modeling is important, and what is design of power system stabilizers, how they are distributed. And in both on the left side NC report, you can see this comparison, but also we did for ourselves in our system, where we compare the response for single mass system and detailed multi-machine that takes into account voltage dynamics. And for 2 different disturbances, you can see the difference in response. Even more, there is a difference having the disturbance at a different location, meaning that it matters also where is your disturbance in the system. And therefore, we wanted to take a closer look in this problem and identify what is the actual impact of load and power system stabilizers to frequency response in order to go back and kind of optimize the HVDC support. So this is some part of the current methodology, where we go step back to the smaller system to understand the fundamentals. We transfer the FCR dynamics of the large system of the Nordic power system to this small one in per unit wise, and then we perform the linearization. And through, of course, we are interested to the transfer function going from power disturbance to the frequency output. And we are interested for this transfer function to be as low as possible. There is also something when we analyze the specific controller and its impact, to analyze the properties of these sub-transfer functions and how they behave with different load models. And here, for example, on the left side, you see that for example, a transfer function from disturbance to center of inertia, that when you increase the constant impedance share in the system, this function is getting decreased, which is natural. When you have more voltage dependent load, it's better for your frequency response. On the other side, you see that the function that relates disturbance and the electrical power output doesn't change so much. Also, at the moment we are analyzing the design of a different PSS, which mainly serve, if they are properly tuned, to improve the small signal stability of the system. And you see here, when you increase the gain of this typical PSS, your system becomes small signal stable. However, what is to note is that PSS could also have impact on this lower frequency range, and it will affect the IFD, and that could be reflected as well on your both plots of your transfer function that you're observing. So basically here we are trying to create an understanding the important factors affecting frequency response, and then combine that with something that HVDC and generators can offer, and kind of create a smart solution. I wouldn't say optimal, because that's a rough word. But especially in power factory, which is not served for some linear control optimization, I think this type of understanding is very important. Thank you for your attention. Looking forward to discussion.
Wow, this was really fast.
Yes, I really want to. So we are a bit.
Sorry, Danilo, you were the last one. But anyway, one thing that I wondered about was because Robert mentioned that about this droop on both sides of an HVDC. If this is something that you have been looking into, or what would be
yes.
the problem?
So far we were looking into only one side droop. So we're only interested in the need of Nordic power system. However, it's we've seen the research work, and it's totally acceptable to set the droop on both sides. I mean, there have been some concerns that if this would work properly, I just think that the power output will be slightly different, but I didn't see that there will cause some kind of issues or stability problems if you have it on both sides. It's just that TSOs have to coordinate what exactly will be the values, as they did in what we saw from the Robert slides, in terms of capacities and droops.
Okay,
I think that's
thanks.
an important point, Danilo, because if you go across Europe, you'll find different maximum losses and different levels of inertia to manage them. So the practical requirements for response are very different. And so as TSOs go around their systems, they do need to be conscious of the levels of response they're offering out between isolated islanded areas, because those areas have less degrees of freedom to accept those sudden demand changes that the response will represent to their systems. But it can be managed and optimized. It's something that is done via allocation at the moment within GB, but over time I can see that becoming a more gradiated project where you're just very, very careful about how you let your response and your speed of response be created between nations, because you need to respect your own limitations.
Yeah, thanks. And there's also one question about linearizing the power system with the renewables. If this is something that you have, that was.
So at the moment, in this small system that we have, of course, when you have big system, a lot of things impact everything. I mean, everything is coupled. So we wanted to kind of step back and look at this small system. And here, when we change the inertia value, for example, we change the generator time constant. Of course, you know that in real system, that's not realistic. I mean, you have to basically implement power converters and decide if they're going to be PQ or PU controlled, which will affect the load, of course, in your frequency response. But in our case here, we don't have renewables implemented. Here we have constant power and constant impedance load. So we have, maybe you can see this constant power load as something that is also connected to converter is a PQ, but you don't see this dynamic. I mean, it's here in simple software, we can set the PQ load, and the linearization works fine or satisfying.
Okay. Yeah, and then Benjamin, there's one question for you. The fact that the HVDC system are essentially transmission systems.
Sorry, should I stop sharing?
Yeah, you can. If you,
if it's needed, I will come back.
You can back. Yeah. Regarding HVDC systems, when you have the grid forming capabilities, I mean, what kind of requirements do you have on the energy from the sending end?
So in effect, that needs to be replicated at the sending end in a mirrored way. So if you've got a very rapid response through the link, which is based on it holding its voltage phaser, and let's say providing a very rapid 20% or so of its rating in response, that needs to be absorbed similarly instantaneously from the remote end, which is perhaps fine if that's a larger system, but if it's a smaller system subject to a greater inertia constraint, then it probably isn't. Other alternatives are to introduce an energy buffer. So that could be either by use of a synchronous condenser or by use of something like a battery or a STATCOM with supercapacitors, which is operating in coordination with the HVDC. And this is where that energy damper is, in a sense, providing the inertia, but it's really providing the voltage reference for the HVDC. So it's acting as a guide rail through the event to the HVDC, informing its performance. And so the HVDC is, rather than following the system, following that device in its delivery of power to a slightly slower extent. And that's a way of lessening the effect of the speed, but you've still got the overall energy supplied. So yes, HVDC most definitely can contribute. And if we're talking about an offshore system, the offshore wind turbines may well be the source of the grid forming supply. And the HVDC is operating in a composite control environment with that. There's a number of options. Okay, thanks.
And Julia, there was a lot of question regarding the loads in your using loads in the frequency for frequency reserves. So maybe you can comment a bit on that. I mean, what type of load are you using? Are there enough units? And yeah.
Yeah, so but I've seen some confusion in the chat about FFR and using loads for FFR. So we have kind of two sub-products, this faster FFR product that was mainly created with storage in mind, though load can participate as well. And then we have this more historical product that was already there, that's load resources providing faster frequency response, which is half a second step response. And for that one, yeah, we have about maybe close to 4 gigawatt of loads subscribed to that. And at any given time, we can see maybe 1,500 megawatt participating. And that's because the 60% limit and how much they get awarded. And so these loads are mainly industrial loads, petrochemical, and then paper industry. They will usually have a number of processes that are equipped with those under frequency relays. And each day they decide which process will be armed for participation in the service so that they don't have same industrial process always participating in the service and, you know, getting tripped. That being said, our frequency falls to 59.7 pretty rarely. Maybe we can see 1 or 2 events a year, if that. But the service they provide, you know, 24/7 every day, and that's a good revenue stream for those industries as well. I hope this answers the question.
Yeah, I think so. And there's actually an additional one about if they actually, if they are committed, are they actually, there? I mean, do they fulfill the commitment? I mean.
Yeah, it's very strict. It's because for them, it's kind of also a good service and good to participate. So on our side, they have to do every other year, they have to do relay testing and provide us with the third-party report saying that, you know, their relay is fine and working and armed at the frequency that we require. And then if there was an actual event, then we can use event information in lieu of this test. And also if event that he goes that deep to 59.7 or lower happens, we always go back and analyze a response from all of those load resources, and we follow up with those that didn't respond as we expected. So it's very strict, and we monitor their performance very closely. And if they don't perform, they can get disqualified for about half a year or until they fix the issues.
Okay. One thing that we kind of wondered about when we looked at the presentation in advance was about the timing of the response between, I think in Texas, it's like the requirement for an FFR unit is 15 minutes. For Robert, in your case, it seems like 30 seconds. And I don't really know about Benjamin's. So maybe you all can comment on this a bit. What is the reason for having these different requirements, or is it the system characteristics, or yeah, whatever?
Mm-hmm. Yeah, maybe I can start. In our system, so apart from this faster frequency response, we have governor response from synchronous generation. We have different types, and they have different speed of response. And so we were afraid that if FFR starts recalling too fast, then we don't have enough primary frequency response to step in and replace. So we basically took this 15 minutes that's from NERC standard as to how fast we are expected to recover from a frequency event. And for the whole duration of event, we wanted to have that FFR available.
Yeah, okay. Robert, do you have any comments?
Yeah, when we made the studies in the Nordics, we saw that it's actually just for the first 5 seconds or so that we need additional power. After that, the FCR the ordinary primary reserve will cover up for the loss. So we saw that it's sufficient to have 5 seconds duration and then a slow ramp, or that they have to provide for 30 seconds and then they could just switch back off again without the ramp. So that's what we saw in our studies. And we think that it was better that we have this short duration, because then we can get more providers and it was sufficient for the system.
Benjamin, what about the situation in the UK?
Yeah, so we found in GP that again you can front load your response and then continue with your dynamic governor action, and that can provide an effective response in a low inertia system. But we also explored under the EFCC project not just predicting the levels of response available, but also predicting the size of the event during the event by measuring its rock-off. And that gives you the ability to layer a number of static and dynamic resources together strategically to deal with the deficit, and then you have a less reliant action of your dynamic responses. So in that arrangement, you can act with a much greater proportion of faster response on your system. But the key there is your rock-offs are different places, so you need to again have that overarching wide area control to organize it. So yeah, these strategies are important, but I think Julia's point about the interfacing between the responses that you're providing is very, very critical, because if you're not careful, you do get these discontinuities, and there are a number of resources who do indeed have trade-offs over the time period as well. So if you're not careful, you give the wrong incentive. So we found that as well.
Okay, thanks. And I think you, Robert, mentioned about HVDC. I got the impression that this is something that you actually utilize as a last resource, the HVDC transmissions for frequency reserve. And I think I know, Julia, you mentioned earlier that you don't have at all HVDC as part of the frequency reserves. And I don't know about you, Benjamin, are you currently using the transmissions links?
Yeah. Yes, so we'll currently use frequency response from interconnectors. So for example, in the famous 9th of August event, you won't find all of the interconnectors in the table which responded and stayed on during the event, because some of them were actually providing frequency response, and so are in a separate table. So it's not uncommon that if you've got interconnectors partially loaded, that they can be a source of response, and they can also have an effect in GP because they're often the focus of the maximum loss on the system. So again, that deload can be beneficial in terms of managing your containment as well. So there's a number of ways in which you can use your interconnectors to help your frequency response.
So, and Robert, what is your opinion about future? Is this something that will be used more regular, or is it more a matter of how to say agree upon with your neighboring countries?
Well, I think the HVDC will play a larger role in the balancing of the system. I really think that we need to implement all the reserves on the HVDC links, and also have the headroom on the HVDC links, and not leave all the capacity to the energy market.
Okay, and Julia, what about Texas, ERCOT?
Yeah, we have very few HVDC links right now. It's all together combined as 1.2 gigawatt, spread around 5 links. And so currently we are not using it for frequency control at all. During emergency times, we can rely on HVDC links to provide support to our system. We have it in our rules, but it's not frequency based. It's based on frequency responsive headroom that we have on our system. We closely monitor frequency responsive headroom. Once it gets lower than a certain amount, then we'll call on HVDC links to provide support. In the future, I'm not sure. We have in plans, there is a large HVDC link that will maybe be built in the future, but there is no discussion yet as to what we're providing frequency control or not.
Okay, thanks. I'm trying to scan the chat about for
just my comment here
yes,
regarding
thanks.
this discussion in the meantime. I mean, for me, at least looking from this point of view where I am now, just as a researcher, it is a bit strange that TSOs are pushing so much for a stepwise response and still want to push for to reduce the inertia in the system. As I showed, I think that could be a problem at some point. Of course, you can always over-dimension the system and then provide certain response, but kind of my concern is that you don't end up in a system with having so many switching elements that when you need under frequency, you switch to give power, then you have over frequency, then you switch down, and then it could be quite hard to track what is happening, especially when you have a big system, because you're not dealing with microsystems. This is just one of, I mean, I prefer the systems if they're like, they can be easily linearized and assessed in that way. I totally understand this is not possible, but maybe it would be good for TSO to push as much as possible in that direction so that you have kind of a continuous control.
Yes. I think the challenge there, Danilo, is whilst I would agree from a theoretical perspective, getting that requisite level of inertia is becoming increasingly more complex to achieve economically, because as we all transition towards our net zero objectives, the number of synchronous generators available to us reduce significantly, and indeed a number of the technologies that are synchronous by default today, if they were being implemented with modern technology, probably wouldn't be. So the case needs to be made for either the markets that inspire that inertia or the technologies that allow that inertia to be present within the market. And the reality is it's probably a combination of those two things that's important. So I think one of the areas which has yet to be fully recognized within the debate around virtual synchronous machines and grid forming technologies is that inherently a control system of a converter is a programmable asset, and the key challenge is rating. So existing converters where deloaders sufficiently can provide a grid forming capability, the extent to which will be necessitatively restricted by the rating, but that capability is going to become ever increasingly important, because if you've got enough of it and you have a market to inspire the mode change that achieves it, then arguably you can achieve your balance that works best between inertia and fast response on the system. And I think it is a balance that you're seeking to achieve.
Thanks. Actually, Benjamin, there was one question regarding your presentation, and that was a bit about why GB is so concerned about the rock-off.
So it basically comes from the size of the loss that we're sustaining in GB to the size of the inertia. So just basically the simple swing equation gives us a very high rock-off in conditions where we're down at that sort of 141 GVA second level. You'll be noticing throughout I've been talking about GVA seconds rather than gigawatt seconds. The reason is deliberate, because increasingly we're having to look at non-megawatt sources, such as sync comps, where this just isn't a meaningful description. And the issue in terms of rock-off is that we have a lot of devices in the GB system which are fitted with what's known as loss of mains protection, and that's because a lot of our generation is in distribution level, and if you have a circuit fault, there's insufficient telemetry to identify the difference between that being an island event and the risk then of switching onto a live system versus that being a disconnection. And so these protections are set up, and then historically they've been on both vector shift, which is essentially monitoring angle movement, and also on rock-off. And those have been quite sensitive protections. So on rock-off, you've had settings of around 0.125 hertz per second, nominally installed in GB. We're currently going through a phase of accelerated replacement, moving those settings to a minimum of 0.5 hertz per second. But still, that's quite low given the scale of our system. On on vector shift, we're trying to get rid of that almost totally. So that a sensitivity of between 6 and 12 degrees over a period of 60 milliseconds simply isn't there. But even by moving that to a sort of 90 degree sensitivity, there's still events on the low inertia system that will move the angle transiently in that sort of area. So we have to be on our guard. So it's really a feature of the legacy of our networks. We've been lucky to have a lot of inertia in the past, and we've seen a lot of generation come at relatively modest size in the interim before we started realizing over time the effect that brings as the inertia falls. And so now it's really whole system solutions that get you to the position where you get the right levels of response on your system. So we're trying to move away from a rock-off limit, but it will take time.
Okay. Thanks. Yeah, I think we are approaching the end of this seminar. It's almost 4:30 here in Sweden at least. There's one question in the Q&A about rating of FFR, power rating. I'm not really sure on exactly what is the meaning. What is it? I mean, in relation to what, or how to interpret it?
Yeah, I thought it maybe about size of resources that participate. Yeah, so as I mentioned, it was designed with storage in mind. Right now, some storage resources still going through qualification for it. We have 10 megawatt and up storage resources already operational. Maybe, if I remember correctly, maybe 100 megawatt is the largest. There is no limit on a single resource that can participate, but as I mentioned in my presentation, there is a limit on total FFR amount that we procure. And we're actually about to start a study to see if there should be a limit on a single resource participating, because the overall amount is so small, maybe we don't want it to be provided by just one or two resources. And so where is this limit? That's something we're trying to determine.
Okay, thanks. I forgot to mention when Danilo started that he is the one who is organizing this seminar. So I would like to address a special thanks to him before the end of the seminar. And good luck with the future studies at KTH.
Thank you. Thank you. It was a pleasure.
So, yeah, I don't know. This is a point where I haven't really thought about how to end this.
I mean, I don't mind staying a bit longer and answering the questions.
Yes, okay, that's very.
I don't know about the other. I don't know about the other panelists, how they feel about it.
I can probably give you about 10 minutes, and then I'll have to disappear.
Yeah, I can take about 10 as well.
All right.
Okay. Yeah, I have kind of lost track of questions, but.
There was one about units for
units for the inertia
that we use. Yeah, so like traditionally you would use seconds for inertia, but we struggled about like what to use as a base, and base should be, for it to be comparable, I guess base should be consistent all the time. And so we decided just to go with energy and physical energy, like kinetic energy terms. And it's still like relative parameter. Inertia megawatt seconds or gigawatt seconds itself doesn't tell anybody anything. It's like Robert mentioned, depends on the size of event that you have, and you know your how much deviation to under frequency load shed that you have, how fast your frequency response is. But for us, it's relative to critical inertia term. So we determined that, you know, critical inertia in energy, kinetic energy terms needs to be this much X, and we want to keep it above that X at all times. So that's where it matters. So units in itself, I guess, doesn't matter anything, but to avoid any confusion with base that's being used, we just went for real kinetic energy units.
I think it could be a bit problematic, because our idea with the common slide and this data was kind of to introduce the audience with the size of the problems the systems are facing in Nordics, GB, and ERCOT, and we don't know if we are going to use we are using the same base. So but then that's why we provided system loading that also gives some kind of, at least this for Nordics, that's they use according to the system loading. This is one kind of measure. But to be fair, I think that the most appropriate is to give per units value for all these type of systems, so people doing research can actually compare the problems. Not just when it comes to inertia, but also disturbance and the power provided, reserved, and so on and so
on. There's also one question about using wind turbine for inertia. It's addressed to Benjamin, but I know also that I think Robert has been looking into this. So maybe you can comment on that a bit, both of you.
So there's often with a wind turbine, there's a trade-off between the aerodynamics of the wind turbine providing very fast response and the lost energy that then needs to be recovered over a secondary response time frame. So we need to be very cautious, again, that we don't confuse fast response with inertial response. But in principle, inertial response is possible from wind turbines, and within GB, at the centre, we supported the Disholock trial of a grid-forming response to the system, which indicated that you can get inertial energy in response to frequency events. And that's essentially by implementing one of these controls, which reserves some of the rating of the converter to respond to the angle change when it occurs. Essentially, it's operating as a voltage source behind an impedance. It will have some kind of current limiting or modulating behavior that ensures that the converter rating is not being exceeded, but in principle it can then act as a relatively stiff voltage source, providing the energy is available behind the turbine at the time. Those approaches are not terribly economic for the wind turbines you'd expect under normal operating conditions, but in situations where the network's been outaged, let's say, or is subject to other constraining factors, or the inertia is simply more important than the energy, which you could easily find at times of very low demand where you've got very few synchronous sources on the system. This is a way of getting through periods of very high converter penetration. So it's a practical solution. I suspect within the Stability Pathfinder, a number of turbines are in there, as well as other forms of converters like batteries. And over time, I'm sure we'll see the right solutions emerge. It becomes harder when you've got HVDC connected wind turbines on multiple connections to the onshore system, because then where do you want your inertia? How do you want your offshore AC system to be coupled to your onshore one? There's lots of interesting control problems to solve, but that's part of the fun of the future. We've got a lot of that coming, but the solution's there.
Yeah. In the Nordic system, are there any plans for this, Robert?
You mean FFR from wind power?
Yes.
So far we haven't seen that, but we were actually having wind in mind when we were designing the requirements for this. So hopefully we will for next year have some wind farm participating in FFR.
Okay. And Benjamin, there's another question regarding HVDC system to provide FFR with additional cost, or if you will consider, for example, if you have energy storage. But I think you mentioned this already as part of this scenario with quite a lot of grid forming converters in.
Yeah, that's it. I mean, the exact reasons for going for those storage options would, of course, be kind of market considerations. And it might be that a number of HVDCs have control systems which can respond fast and stably based on where they're connected. But what I would say is that's something that changes dynamically over time. So in GB, we don't have any particular requirements for minimum short circuit level. So whilst we might be trying to hold the national inertia to a particular level, the location of that inertia, the resultant short circuit levels that evolve, can change a lot over time. So there's been places where the inertia and short circuit level contributions have fallen by more than 20%. And that means that a design of a control system today might not be robust against the same challenges tomorrow. And that's really for a user to watch and maintain as their connections evolve over time, which sounds harsh, but that's the sort of environment we're in. So you just need to be very cautious of those non-inertial techniques in isolation. You can add control layers, but normally what you do when you do that is you add tuning challenges then for operating in higher inertia environments, and markets being markets, the levels of inertia, the levels of contribution change in location and scale over the course of a year. So what works for one situation may not be appropriate for another. So it's not a straightforward strategy to get rid of the storage element and still provide something that's inertial. So I think we all have to be really cautious about fast response in isolation.
Thanks. Yeah. Okay.
That's it, right?
Yes, I think so. I think that it's probably missed some questions, but maybe we can review them afterwards and post something on the website.
Can I say again, thank you to all panelists for all the people who are attending this webinar. It was really nice to join around the forces from Nordic to US and Great Britain. It's really interesting for me, and it was a pleasure being a part of the webinar.
And thank you, Danilo, for organizing this.
Thank you. Thanks, everyone.
Yeah.
Thank you.
Okay.
Bye.
Bye.
Bye-bye.
Thank you all.
Thank you, Inger. Thank you a lot. So, Inger, I stopped the recording. Let's see what will happen. I don't know about should we take how we can save the.
Yeah, I was thinking.
Save chat. Okay, I press something. Chat save. Let's see.
Because there's also
there are
questions. Sorry for.
There are some questions for. I hope this is saved. And then I don't know. I think we answered most of it. Of course, we couldn't catch all of them, but yeah.
It was a bit. It became more difficult when some were answered, some were not, and then.
Yes. Okay, Matas is still here.
I can take a screenshot of the questions here.
Yeah, we have some questions in Q&A. I don't know if we managed to answer all of them.
I think we have. Some of them came in both places. This MCP slide mode, it's not. I did not ask that one. Non-linear control approach will have any significant on the existing fast frequency control. But I might be that one is also in the chat, and then yeah.
All right. Thank you again.
I did. Yeah, it's okay. I did not see the chat when I presented my screen because I think that was behind the PDF file, so I didn't want to disturb, and then I didn't see the help on how to enlarge it. So yeah, I'm sorry about that.
It happens. I mean, it's a live webinar. Okay, so we'll be in contact. I will see to send the recordings and to see the chat and to see the questions, and if we can answer something through the website and so on, and then to put slides, and so people can access and take another look when they have time. All right.
Yes.
Then that's it, right?
Yeah, I think so. Thanks.
All right. Thanks.
Good job, Benjamin. Yeah.
Thanks. Bye.
Bye.